supposedly I'm live. Okay, back to this for now. So a couple of things, just again, like the question of when to do the office hours first, just 2 seconds. What was the time to meet or when to meet? This one. So what do we have? So I still suggest a slot which is like 4:30 to, let's say, 5:30, but people who are not available in this slot 4:30, like Dominic, Axel, Alex, and Raja are drawn. So are you guys available at like 5:30? Like, I mean, there are two options. Either drop three, say, okay, forget it, not everyone can participate. Alternative option is to do it like alternating every other week in the different times. So we either take Tuesday and Thursday, and I will switch weeks. And then at least people can attend every other week. People who have a conflict, like something like this, but it's the same people. So I think you should just do it Thursday. Like Friday, I would be happy to do a Friday, but I'm gone multiple Fridays afternoon.
Yeah, I think you can just do it Thursday, and like it's me and 2 other people that are unavailable. I'm sure I could just email you
or I can do like
really make myself available.
But I'm honestly pretty flexible in this green slots. Friday is just I just don't want, like, now it's 3 people. I don't want to drop people. So what's the Alex? Do we have Alex here? No? Someone who's unavailable. So only Dominic is in person. You? Right. Or
I can't do Tuesdays and from 3 to 5.
At 5:30. So then let's do it like 4:30 to 5:30 and see yeah, okay, then this works. Yeah. And who is the third person?
Alex.
Yeah.
Or you, Alex.
Okay, sure. That's not helpful. Okay, then 4:30. Okay, sure. Then 4:30 to 5:30, potentially up until 6. I mean, I have time if needed, right? It works. And I like it. So there's always Zoom, so you can also Zoom. That seems that it works, people. And Dominic will catch me if he needs. Okay, so now back to the discussion which we had when I showed up. So again, one more time, which is a little unusual. Let me just maybe switch to this diagram, which no, let's verify that everyone understands. Okay, the question is the following. Alex says, okay, I want to map reasons for why IDT and GDT, no, and let's say TSS exists, right? Exists. So let's just walk one more time. So imagine we have a GDT. Like let's start with IDT. Interruptive triplet table. What is the reason? Why do we need it? What's the main reason? Let's ask the question this way.
Need to have entries which define how do we handle different.
Agree, and I would argue the main reason, even if you're working on a way simpler CPU without privilege levels or anything like that, the most important thing which you care about is the entry point of the handler, right? So it's a handler is a routine. Like we will take a look at how we can write one. Maybe some people remember from x86, so it's like typically some assembly prologue, and then this regular C for the rest of it, right? So that's the main reason, right? So it makes sense. Pointer to the handler. On Intel CPUs and many other CPUs, you have this concept of privilege levels, right? And you say, look, guys, what if I'm running at something like privilege level 3, which is user? And really, my handler here accesses kernel data structures, like, I don't know, current process may have a pointer to a current thread. Whatnot, like maybe it's a list of threads, right? Because the process will have a list, right? So of course, all of these data structures, they are in kernel memory. So the page table and segmentation, let's say page table is set up in such a manner that they are accessible from privilege level 0, right? So because otherwise user can just override it, right? Okay, so we say, look, we need to switch. So on top of the fact that we have to jump to the entry of the handler, we somehow need to encode the fact that we have to switch privilege level from 3 to 0. Agree? Switch into the kernel. Guys, concentrate. Intel in general encodes privilege levels inside local descriptor table. That's why GDT exists. So Intel will say, look, there will be a dummy entry 0. I don't know why it's there. But other than that, we expect that the kernel configures 2 entries for the kernel and 2 entries for the user. These entries, one will be for the code, one will be for the data. This also will be one for the code, one for the data. And like the kernel entries will be configured with privilege level 0, like it's a 2-bit field 0, and these will be configured with privilege level 3, right? Right. And when you very first time, when you put it on the machine, very first time you exit in user level. Do you remember how we exit into the user level? Which instruction do we use? IRET, exactly. That's one way. There are other ways, but let's say IRET. IRET says, okay, we will choose an entry for the code segment from GDT, and that's why we start running at privilege level 3, right? And then we run at privilege level 3 for a while, and then assume timer interrupt, assuming this is a timer, vector 32 comes in. You say, look, I want to switch back to the user level, right? And so specifically, there will be a pointer, I think it's called like segment selector, code segment, which will choose an entry from GDT, which is specifically a code entry. Code means that it's an executable flag, and this is writable or readable only. This is executable, this is writable, for example. And you're back in 0, right? That's why GDT exists. Make sense? So it encodes privilege levels. In addition to all of it, there is this problem that you don't trust the value of the stack pointer, or RSP, if you like. And so you also need to figure out where to get the stack for processing the interrupts, essentially for running the handler, right? And the stack, let's say, is just some other page in kernel memory, right? Which is what pre-allocated. And we say, look, but how can we allocate this? And we were thinking that maybe you can design a CPU which has a separate like RSP 0, and this is RSP 3, maybe like for privilege level 0, there is a register which is not accessible by instructions from PL3, but that's not what Intel does. So I think ARM does something similar, right? And so we say, look, in order to locate this stack, we'll be using another data structure. Here will be another entry, a pointer to a TSS, and specifically, it will go to TSS. And TSS has a bunch of other fields, but up until now, we care only about 2 fields, and this one field is a pointer to this stack. I was trying to land on it. Yes, makes sense? And the second field, this is the actual pointer, RSP, and this one will be a stack segment. So this one is just a number which will choose kernel data entry from the GDT, right? That's how everything is connected. Make sense? Any questions?
We can, I need to pass some arguments from the user stack to handle the handler needs certain arguments for the exception.
Uh-huh.
And I need to pass it from, I believe, the user stack to the limits. So I just like toggle with those stack pointers and push them on the front stack. Is that right?
Okay, that's a good question. So let's talk a little bit about it. Imagine there is also a user stack, right? Which was used when the PL3 was running, right? So this ESP was specifically pointing to somewhere on this stack, right? The question you're asking is, how do you pass arguments? And I mean, it's a little overloaded because normally if it's a page fault, user doesn't pass any arguments. If it's a timer, user doesn't pass any arguments. In general, if it's a hardware level event user doesn't pass an argument, right? But imagine when we also use this exception mechanism or interrupt mechanism for implementing a syscall, like x6 does. So user involved int, let's say x40, that's just a number which x6 picks, but you can pick any unreserved number. And you say, look, after that, of course, it will go through the interrupt description table, choose this entry number x40, follows the same kind of thingy, but it's a different handler, right? The stack is the same, right? But the handler will be different potential. Maybe it's the same handler, but it's unlikely. So essentially, this pointer will be pointing to a handler in the kernel, which handles this syscall. Makes sense, right? The question, like again, some assembly stop here, and C code to implement the rest of it. The question, how do you pass arguments? And again, there's a range of design choices here. You can say, look, maybe I can pass everything in registers. Because why not? That's a convention. You say, look, before invoking this int x40, we say, look, we'll move something in the EAX register or RAX, like, right? Using Intel or whatever, like some calling convention, right? Sure, that works. Then you just essentially, as part of this transition, the expectation is that this handler, this prologue will save the values of R, like user registers on the kernel stack, and RAX will show up somewhere here in all the other registers, right? And you can access them. You say, look, but what if I'm running out of space in registers and I wanna, it's a bigger object, I can pass it really on a stack here, right? And then you say, look, again, like you can do whatever you want, but right, any convention, but in x6 actually everything was passed on a stack, right? So arg0 was passed on a stack as well, right? So obviously the value of the RSP pointer itself, user RSP, will get saved on this stack, right? As part of the entry into the handler. We just want to preserve the user registers on this kernel stack to make sure that we can access these values, specifically for the reason that we can access this value, drop a different color, and which will point back right here, and so we can read this argument, right? That's the mechanism. So essentially, in the prologue of the handler, we will take a look today. We'll push all the user registers, which were obviously in silicon, on the kernel stack here, and then access them from this stack. We'll pass this stack to the handler, to the C handler, so we can actually access those arguments.
You think that there's an entry which points to the user stack, right? And then we can access the arguments from there. Is that what it is?
No, like, yeah, originally RSP was a register hardware, right?
Right.
Actually, when the interrupt transition happens, right? It saves the RSP when you cross privilege levels, right? So it will be saved by the hardware itself on this kernel stack. And so this is how, if we pass the pointer to this kernel stack, we can later access it from C or Rust. And we can access the value of the RSP on this, saved on this stack, go to this stack and read this argument and read the entire user stack from the kernel. Make sense?
Yeah. So when we extend this side, then it boils down to the kernel reading from the user stack, which is the whole point of making a new stack was we don't trust that.
Ah, okay, that's a great question. Okay, great observation. Okay, what Manik is saying, guys, we just said we don't trust the kernel stack because it may point to some garbage page, right? How come suddenly we are reading the kernel? We don't trust the user stack. How come we, if user passes an argument, how come we are reading this argument from the user stack and not worry that the stack is actually not present? So who can tell me the answer? That's a great observation. It's very logical. It's so logical that I forgot to mention. But I mean, people who did x86, they know it. Everyone in this room. Alex.
Like, isn't there like two layers to Syscall and x86 for exactly that reason? Like, it's like there's an interface that like checks the arguments for validity and then actually steps into space, something like that.
Correct. So we somehow validate the arguments. How do we do this? And I will come back and explain it one more time. Do you remember how?
Yeah.
No, okay. But that's essentially, that's the intuition is this. We will never blindly access this pointer from the kernel because it's unsafe. It can point to null, it can point to a map page, the kernel will crash, and then like might stop working, right? So what the kernel is doing, it uses a very careful wrapper around this access, which validates that this page is actually correct. And you can go differently about it. x86 makes an assumption that all the pages from 0 to proc size are mapped, and it just simply checks that this value is lower than proc size, or specifically it's lower, like on this side, it's higher than 0 and lower than proc size, and plus the object which we're currently trying to access is fully under proc size because it can be like half of it is inside, half of it is outside, right? Of course, this is a very simplistic construction of the user address space, because what if it has holes and whatnot, like in a modern operating system like on Linux, there is like really the address space is very, very, you can say holy. And then there is no simple check like this. It actually accesses, and if there is a page fault, then it does the walk. It maintains enough metadata about the address space, what is mapped, what is unmapped, and says, okay, look, if it's the page fault and this page was supposed to be mapped, but maybe page fault or like that maybe swapped out, then we will swap it back in. And if the user really tries to like to fool you into accessing some other memory or maybe kernel memory, then you kill the process, right? So, but essentially it's a wrapper. Let me come back to your question again. You're asking, well, hold on, like, but can't we do the same wrapper on the entry to syscall? Okay, can we? No, like I explained that if we accessing user arguments, we use some kind of a safe wrapper code, which allows us to safely access user memory, right? So that's why it's okay to access the user stack page when we are inside the syscall handler here. The question is like, can we do a similar wrapper? Again, back to this Monovik's question. So what is this idea? Why we don't trust the user stack on entry into the syscall, into the interrupt handler, but suddenly later on we can build the wrapper. Do you understand what I'm trying to ask? Does anyone else understand?
I don't know. I have a guess.
Okay, tell me, what's the guess?
Is it, do you like fork and like treat it as a user process and the stuff and show it anyway?
No, hold on. Like work, no. Like it's also important to think about it clearly. Okay, Manovik, do you understand what I'm asking?
Yeah.
So why why not to like essentially implement a wrapper which just uses the user stack after checking that it's mapped and stuff when we enter into the syscall handler? Why did we say that we need a stack?
Because we also don't want to leave kernel data in the user stack later for.
That's a great, well, another great observation from, yeah, Soham says, okay, guys, by the way, the moment we start executing kernel handler, we start pushing something on a stack, right? And the stack is in user memory, right? So maybe we pushed some like whatever, a password as part of the syscall because we were decrypting the disk or something. If we push it on this stack, then if our system supports multi-threading, right, then another thread which runs in the same address space can actually look at this data and steal it, right? So the stack switch is also required for security reasons, right? And we'll come back to this later on. And again, yeah, that's a great thinking. So that's one way we need to switch for security reasons because we cannot push sensitive kernel data on the user stack. Even not sensitive, just imagine you push something, but with the goal to restore later, another thread just overwrites it, right? With like zeros or something, or maybe something, and then you like return to an address which completely doesn't exist.
So I know in the original V5, it would copy the arguments into kernel space. Do we have to do that? I know it's probably necessary for lifetime reasons. Like, if you transfer again into user space, then it could modify that address, and then it would be out of sync with what the kernel is.
Possible. I don't know this. Like, if you send me a link and say, okay, I read it here and here, I will go and you're saying that there is a time of check, time of use attack, and you're saying that, yeah, you're probably right. So, and maybe, I mean, if we start from, but you're right. So if you blindly trust this value and that it trusts that this value will not change for the duration of a system call, that's naive because another thread can change the value and might confuse it. It's the time of check, time of use attack, right? And so you have to copy it in a safe place as well. That's true. I mean, x86 doesn't do it probably, or does it, but doesn't emphasize it because it doesn't support multi-threading. But I just wanted to come back to this question. Okay, if we have a safe wrapper which allows us to access user stack, why? Like, okay, again, Soham said, okay, we need to switch for security reason, but what prevents us from like, why do we really need this kernel stack?
The process stack might be close to kernel.
That's another great idea.
The kernel might just not want to do the housekeeping to ensure recipe space. So he's using a fresh stack.
That's also true, but the answer is actually simpler because yeah, the answer is simpler. The very first 5 arguments are pushed by the hardware, right? The hardware is very naive. It just pushes. Hardware doesn't know how to implement this wrapper. It's all semantics of your kernel. It cannot do any checks. It just blindly pushes 5 values here, right? So, and that's why essentially the hardware silicon itself doesn't know anything about what you're running, what kind of kernel and anything, right? It just needs a pointer to the stack and will just push 5 values, right? That's why we switched to a safe stack, which is kernel. But other reasons are also correct. So when you say, look, you have to switch to protect from protect the stack from user access and stuff like that, right? Okay, that explains what you asked. Like, everyone else reasonable? Okay, any other questions? Good. So Alex, you you feel better. Okay, and anyone else now? We understand what the role of these data structures now kind of has to be by heart at this point, right? Okay, good. Yeah.
You said the hardware, yeah, it doesn't know the implementation of the wrapper.
Mm-hmm.
Can that be a part of
No, right. But the hardware has to save at least E flags. It should at least say RS instruction pointer, RIP, and a code segment, right? The old ones. And you need some script space where to save it before you start running code, right? So, and there's probably a way to solve it by saying, look, we have some script registers on the CPU, and you can start writing your handler, and temporarily other interrupts are disabled because there is like registers are finite, only one script space, right? But I think the trick with the stack makes sense. Okay, so we good on this? A couple of additional things back to what Alex was asking is the following. So this also, the field inside the interrupt descriptor table, two important fields here. One controls whether the further interrupts are enabled or not on transition, right? And this field can, like, because if you set it to 1, I think, then immediately disables further interrupts. And after that, you can only receive a non-maskable interrupt, right? Or if you don't set it, then, you know, you go into the handler, but interrupts are still on, and you can have another interrupt, right? That's one important field. And the second important field is the privilege level from which this interrupt can be invoked. So for example, for this one, which we allow user to invoke, we'll set it to 3. But for all others, it will be set to 0. Make sure that user cannot confuse us, confuse the kernel invoking something like int whatever, 2, for example, non-maskable interrupt, right? So that's also a role of the interrupt descriptor table. It's kind of like part of the security story, which prevents the user from abusing the kernel, right? Makes sense? Okay, so now, and maybe I missed something, but more or less, this is it, right? So, okay, I wanted to get back to talking about how to build those handlers, because it turns out it's a little like more involved. And it's not like super involved, but still makes sense to talk through a couple of things for how like things which are needed for building those things in Rust. So how can we do it? Okay, again, just make sure that we understand which data structures are needed. We need to configure GDT, IDT, and ESS, right? Then we need to write the handlers, and specifically what we need here is we need to learn how to carefully interface, what kind of awesome assembly code is needed to carefully interface with the stack, which the hardware pushes for us, right? Because sometimes they push like an error code, depending on the privilege level, switch or not. It pushes either 5 arguments or 3 arguments, right? So that's our plan. So, okay, sure. In roughly speaking, it doesn't matter in what order we're going to be doing it, right? So we say, look, just these data structures, let's just understand how they work. And the last thing, which we will not be able to do today, we also need to configure an interrupt controller. And again, like probably we will skip a lot of details here, but at least we will talk about what this controller is. Essentially, it's a piece of hardware, and you kind of like you were configuring serial line or VGA. You tell it, okay, please send interrupts and follow specific set of rules, right? Okay, so now one thing from last time, which we kind of missed last time. I mean, we didn't miss, we talked about it. Who can tell me like which data structures are CPU specific and which are global for the entire kernel, for the entire system? Which are per CPU? Dominic, you. Otherwise, you're sleeping.
I don't know. I guess so.
Well, I know the interrupt stripping table is defined by the Intel architecture. So I'm assuming that's, I wouldn't say it's per CPU, but I'm guessing they all have the same one.
Hold on, like, again, like, it's important to understand what I'm trying to ask, right? Remember, we talked about it last time. And we said, look, some of the data structures have to be private to a core or a CPU. And there was a reason why. I'll give you a hint. Because on simultaneously on multiple cores, interrupts can happen, right? So you probably at least need a stack per core, right? A kernel stack per process, per core. What else is per CPU? What else? Which, since we need a kernel stack, we need a TSS because it has a pointer to this stack, right?
And the GDT.
And the GDP because it has a pointer to the TSS. Agreed. So per CPU. And this one can, it seems to me, can be global. Agree? So there's just one instance per system, right? Just to make sure that when we write code, we understand why, right? So when we boot on the boot CPU, we initialize one global interrupt descriptor table, then we're gonna load it on all the CPUs. However, each time we start a new CPU, like we first look at, we're gonna look at the CPU number 0, which is a bootstrap CPU. We will connect, we will load the GDT. Essentially, on each CPU, we will load a private instance of GDT, private instance of TSS. And of course, every time we will be switching to a new thread, we'll be updating this field in the TSS to point to a specific kernel thread, right? Make sense?
Yeah, I was actually gonna ask, so, more accurate to say that each TSS per CPU, the stack is per thread.
Correct. Yeah, per thread.
Threads, CPUs.
Correct. Yeah. I agree with this. Yeah, I was thinking the same, but yeah, didn't want to confuse people. Now makes sense. Agree with this? Okay. One practical logistical issue: how to implement something per CPU. How can we do this?
I mean, it'll all be data structures anyway, so I guess if we can pin a process to a core, then we can have like per core data structures. Because even like when we initialize CPUs, there are also the data structures.
Yeah, there are multiple ways, but we'll do a simple approach. We will say that we'll have an array of those data structures, and we will be resolving an instance of this array with the CPU ID. We can get the CPU ID from the local programmable interrupt controller, but maybe we also will have it. Actually, we will do a simplification optimization, and we'll put it inside we'll put a pointer to this and instance in the array in the GS register. And so we will be implement GS relative address. Right? Makes sense. Let me just show you quickly. I'm running out of space, but I can erase here. I'll take a question in a second. So at a high level, what we need to do is have an array. We can put anything inside. Like this element of the array will be for CPU 0, this one for CPU 1, this one for CPU 2. What we put inside is our own decision, and we will, like, in this system, we will put like at least GDT and TSS, right? And they will be sitting like somewhere here. And what we will be doing on each CPU, we will configure GS register to have a base to point, like GS on CPU 0 will point right here. GS on CPU 2 on CPU 1 will point to this instance of this data structure, second element or whatever, first element in the array. Make sense? And then everything, if we want to access inside this data structure, we use GS relative addressing, some offset And this allows us to say, look, GS is a fast register like any other general purpose register, can be accessed within the same cycle, because like x86 does this trick that they say, look, every time we want to access a local copy of this data structure, we will ask the programmable interrupt controller which CPU we're running on, but it's a little slow. I don't exactly know how many cycles, but on realistic system, it's not a practical solution. That's why we will use GS. Make sense? Question. Correct.
But it's not configurable that you don't need to write a driver so that you get the hardware to push those 5 arguments to the kernel.
Yeah.
So like, what does it? Like, do we care about what it controls, or are we just gonna?
That's a good question, and I'm not an expert, but I will try to learn more by next week. So roughly speaking, it can allow it configures the interrupt delivery. Just even says, okay, which hardware events, the ones which are reserved by the CPU, you cannot remap, right? The first 32, but the others like timer and everything else, I think you can remap. And there is also a mode, like different things, like whether deliver things as non-maskable interrupt through a vector 2, stuff like that. But also even like if I remember correctly, the protocol, how you acknowledge the fact that you received an interrupt and you're ready to receive next, stuff like this. But let me read more. I always was a level above. I mean, I don't know where we stay. But yeah, we'll at least like the super cute modern features allow you to like route interrupts to specific cores and stuff like that, if I understand correctly. But let me read on it. But it also has like allows you to say CPU. You can ask for a CPU ID and it tells you on which CPU you're currently running. But it's slow. That's why we're gonna ask just once and then always be using GS.
The array technique for the GSS, for the GDB and the DSS, we would have to have sufficient padding, right, to prevent like cache coherence issues.
Right, correct. Yeah, yeah. And also that's a great question. So you have to be careful to make sure that you don't have coherence, not issues, but slowdowns, performance issues. That's right. Actually, in this code base, I don't know if it's done. Let's take a look. The question is like, if you accessing those data structures from 2 different CPUs, like from CPU 0 and from CPU 1, and they are physically different, right? So they're connected with the bus, with the like cache coherent bus. If it so happened that on the edge between these 2 data structures, they get located in the same cache line, this cache line starts bouncing back and forth between hardware cores, and it significantly slows the access, which means that you have to make sure that you pad them enough so that they don't share a cache line. Okay, so let's quickly take a look at this trick, how we can do this the CPU array. And again, it's one way to do it. So again, this is where it gets a little complicated, but understanding one way is enough to keep going and make sure that you can build a system which can support any. Because realistically, what's done on Linux and Rust can also do it, and I did it in other operating systems. You can use a specific compiler flag, and compiler just, instead of like statically managing this array, compiler just creates a special data section in the code, like thread local data section. And then it's just when you load the kernel, you create like X instances, X is equals to the number of CPU cores, and then it runs. Like, so it's a little bit more elegant and automatic because you can have this thread local variables all over the place in your code. You don't have to like bundle them carefully together like we do here, but then it's all bundled by the compiler, and it just at the time of loading, you just allocate space. But the same trick works for GS. And GS, the trick with GS also, like compiler does it automatically. But here we do it a little bit more manually. So look at the code. So what we do here, we say, look, we have an array of CPUs. each of those like the CPU data structure contains what's this? It's there. How we define it? We can define it like this. So this is a struct CPU aligned to be at the page. So essentially alignment is there. And here, this is a non-elegant piece that we did it manually. We say, look, manually we will put all the fields which we believe have to be like per CPU, right? And specifically what we care about is the global descriptor table and a task TSS, right? And others, but just for now, like forget about them. But essentially, these two is the ones which we discussed we need per CPU. Agree with this? Here now we need a little bit of plumbing to make sure that we can actually kind of access this data structure in some elegant way. In something like C, you can probably use C macros to essentially say, look, we will carefully access through GS. Here we do this trick. We actually we store a pointer to itself. In each of these data structures, we will be storing pointer to itself. It's again not necessarily the only way to build it, but essentially the idea here is this, that we let's take a look at how we initialize. So essentially, when we initialize a specific CPU data structure, we take a CPU ID as an argument, take a array element of CPU ID into this CPU variable, get its address, assign self pointer to the address, assign CPU ID to the address. This later on, because later on you just like GS will be pointing to this one, right? But you will not be able to, like, you want to know which CPU ID you're running on, you still need this information, right? Here we assign like just a syscall stack. It doesn't matter for now, but essentially here, what we're doing here, we're using this CPU instruction, which writes a specific model specific register MSR, which is specifically this number, which controls the base of the GS register, right? And we just write this address, right? Make sense? So at this point, GS points on this specific CPU, GS points to the beginning of this data structure. Make sense? Now, when we want to access this, like for example, you say, look, if you want to get okay, what's the reason why we're saving this pointer? It's just that if I understand correctly, you cannot easily read the GS base value back. Actually, you probably can, and maybe Zafang is overdoing it, but essentially there is an MSR which allows you to read GS, but like it's like once you roll the GS through the MSR, you probably can only read it through a different MSR. So that's why he has a pointer to itself. And so what he does here is he says, okay, look, if I want to get the address of this current data structure, I will read the self PTR field, right? Because this is the name of the field which points to itself, this field, right? Self PTR. You ask a question, okay, but how do you read it? Because you said that it's addressable through the GS. And so for that, we use the collection of macros. So for example, this one, read current CPU field, is a macro, which essentially uses another macro, read current CPU offset. And this read current CPU offset is essentially a macro which uses assembly internally. And this is what it does. So it uses this GS relative addressing. So it's essentially just says, okay, GS, and it works exactly as you imagine. So GS plus that offset. So if GS points here plus the offset maybe like 8 bytes, will read the second field. In this specific example, offset will be 0 because it's the very first field of this data structure, right? And it returns the value. There is a little bit of unpleasant kind of like syntax, which you have to like either look up or, I mean, it's not the most intuitive syntax to write assembly, right? But makes sense essentially. So this macro reads CPU offset and allows us to read like a per CPU instance of this data structure. Makes sense. So like when we use it, it looks something like, Well, that's a meaningful examples. Like when you use get CPU ID, you just read current CPU field and you pass the field name ID, and then just read it from the structure. So it's kind of elegant, right? In C, you would be using macro. This is what Linux does. So Linux has a per CPU macro, which roughly speaking does the same internally. Make sense? Okay, once we have this, like other things we need, IDT, GDT, TSS, right? Okay, let's take a look at how can we build this. So we looked a little bit last time at the GDT. Let's quickly come back. Do we remember what are the minimal entries in the GDT which we need? We need what? We lost.
Oh, you said it was.
Because of the double. No, actually, I mean, it's correct. It's lost in this implementation and just a big difference.
Yeah, no, you need.
It can be anywhere. It just cannot be zero because zero is somehow special for it. But you're right.
Like if we write GDT, why do we?
This is you as a designer, you just pick any position. It doesn't matter. It only thing that numbers have to match. This is a number and it has to match this entry. So roughly speaking, if this is zero, this will point to number one, right? For the stack segment, it will point to entry number two. But we could configure it differently. As long as the entries match, that's fine. GDT is not defined by the hardware. It's all up to you. And you can put as many entries as you need. But essentially, the minimal entries which you need are here on the board. So we need dummy zero, code data for your kernel, code data for user, and a TSS, which is a double entry. It's, I think on this system, like it's just a coincidence that this is in this specific order. That just doesn't matter, honestly. We can take a look at, let me quickly look up the definition of GDT for us. Where is it? Let's see. Sure. Oh, here, yeah, correct. So we just say like this is defined by the hardware. It says okay, it's a null entry, and we try to be well typed, meaning that just instead of like have an array of it just helps you later on in life. So like all the entries are GDT entry and the TSS is a double entry, right? Makes sense. So it's the beauty of a safe language. It will help you. And after that, you know, this is kind of unsafe because you say, look, I have to make this connection. So I have to make sure that indices will match, right? So kernel data will be 1, kernel code will be, it will be 2. So I flipped this to, I didn't remember that. Again, user data, user code, TSS. And then those entries itself, they're not just blindly numbers. So they are actually also defined by the Intel, right? They're like specific types. And so we actually create those with this. They conform to this segment selector type. And the segment selector is, I don't know if we defined it ourselves. So we can take a look. No, we'll probably take it from somewhere. We take it from x86 crate, right? So it's defined there. You can define yourself or you can take it from a crate. Somewhere. But the idea is that you have to make sure that these numbers match. And essentially what I do here, or Jafang does, is he says, okay, look, I will initialize them correctly. What's important here is that he uses those, he says, okay, this will go with privilege 3. This will go with privilege ring 0, right? And this will essentially uses a specific number to make sure that, like, where are we? I don't think this is entirely what I wanted to say correct. So, but essentially the high level story that these numbers have to match, right? So because you later put them, like when you put these, you will put this user CS or kernel CS specifically, like this, where will this go? Do you guys, can anyone tell me which GDT, IDT, where will it go? Just say GDT. This thing will actually, it will sit, if I understand correctly, it will sit here in it will sit here and will point to the entry, the GDT. So it's like it's a selector. I might be wrong. The point is that like make sure that whatever goes here has a specific type, and this type is slightly different. So let me show you. So when we initialize GDT, we specifically like this will be a GDT entry type. So limit, offset, offset low, offset medium, offset high, stuff like that. And we initialize those explicitly when we create a new GDT. Let me show you here. Somewhere here, for example. So like kernel code is this thing. This goes inside the GDT, right? And what's important, as we were saying, that's again privilege 0, executable is true, writable is true, and it's a long mode flag in the access flags, right? But those guys will go into, like, let me show you. If we take quickly switch to IDT, then when we initialize IDT, we will here. But anyway, so you will have to go there. But okay, modular some minor misunderstanding. GDT is clear, right? So we wrote GDT with this whatever 5 entries. Like everything is there. What's probably important there is just quickly take a look at TSS. TSS is nothing super special, but we'll have a pointer. To the TSS address, essentially, right? So, and where do we get the TSS address from? We get it, we can take a look here somewhere at the beginning of this function. So we get it here. So essentially just like quickly, just to make sure that we understand it. So this one gets an instance of this CPU variable right from the current CPU. So we have a CPU, and then later we'll be using it. TSS, this code initializes some other stacks. We're going to talk about them, but essentially what we care about here is that it's this RSP0 address. This is the kernel stack address, which we essentially get from here, right? And we essentially set it. And then we have this TSS address, and the TSS address will go in the TSS field and show up, where is it? Here, right? Makes sense? So we connected this one, the TSS entry to TSS. Makes sense? And I will post this code, not specifically the code, but bits of this code online, but your goal will be, in the homework will be to connect this. Okay, this is clear, Jerry. That's a good question. So, like, imagine later on, you're running on some kind of a core. No. When you run on this core, you say, look, I want to access my local version of, imagine it's a TSS field, whatever, right? TSS variable. There will be a TSS here, there will be a TSS here, there will be a TSS here, right? At this point in your code, how do you know the core ID on which you're running? Let's say it's like 0, 1, 2, let's say it's 2. How do you know that you're running on 2? Because if you know the number 2, then you go into the, like you have a global variable for this array, you offset into like second element, do some offset and get the address of this specific data structure, right? Okay, so there are two ways to do it. One is to ask the hardware, like essentially go and ask LATIC, local advanced programmable interrupt controller, which CPU I'm running on. It will return you two. It's a little slow in practice, so the XV6 doesn't. Instead, we say, look, we will ask, when we will be initializing this core, we either already know the number or we will ask the LATIC once, and then we do this computation once and put this address in the local GS, because GS is per core. So each core will have its own instance of GS and will point to the entry in this array, right? After that, everything is relative. In this point in the code, you just say GS relative to GS offset, some offset here, and it gives you immediately lands you on this instance. Make sense? So it's a performance optimization, because GS is a fast register like any other general register. It's accessible in the same cycle as everything else. So how?
Are we also using this data structure to keep stuff like process tables?
No, we don't need, because and again, it's a design choice, but process table will be global under a mutex, but those things are running in parallel like per core. Okay, so we got this. Now a little bit of everything else is probably more or less boilerplate. What I wanted to stop and spend some time here on is on the IDT. The question which I have is that, which I asked a couple of days ago. How can we connect? I mean, the end goal is to write a pointer to the handler in the IDT. I mean, you say IDT is probably the same as GDT, well typed. So we just assign a number, and the hardware will jump to this number, to this address in memory, which contains the handler, right? The question is like, what's the connection between low-level hardware interface, which pushes 5 things on the stack, but sometimes it pushes 6, and sometimes it pushes 3 or 4, right? Depends on like whether the privilege change was happening, whether the interrupt handler pushes the error code or not, right? What's the interface between C and assembly and the hardware? How to build this? Anyone knows?
Well, for the calling convention, you can't clobber any of the user's registers. So you have to use a special calling convention for interrupts.
Correct. And what will this calling convention be?
I'm pretty sure it's just xturn x86.
Okay, let me explain what you said for everyone else. What Talia is saying is the following. When we start executing this handler, hardware did not save any of the user registers like RAX, RBX, and so on, right? None of it is saved. The only thing which was saved RAP and RSP, potentially if we moved between user and kernel, and also CS, E flags, or R flags. And what stack, right? So clearly, before doing anything in the handler, we need to save all these registers. So, right, roughly speaking, on entry to the handler, we have to push all these general purpose registers. Agree with this? This is the calling convention, because calling convention for a normal system 5 ABI is that some registers can be clobbered, like overwritten, and the caller has to restore them, and some don't. But here the calling convention is that all of them has to be saved and restored. Agree? Right? Make sense? Okay, sure. Philip, I think, actually pushed a special calling convention into the Rust language. I think it's a style SS. It's called x86 something underscore interrupt. And what Philip is saying, if you essentially write a function like this in your code, which will be x86.
I think it might be. He has a newer block.
No, that's been around. Oh, sorry. Let's take a look at. Let me just find one example. Just like this. This will work. So this is the convention, right? x86 interrupt. And essentially, if you write a function, something like which implements this convention, then the compiler will automatically generate saving and restoring of registers, all the general registers on entry to this routine. I mean, probably a good way to just find one of these, like for example, this one, double fold. Do I have an implementation? I have it. So like, for example, I have a double fold handler, and essentially, did you get it? It's like a calling convention. So if you say, look, this function follows this calling convention, the compiler will save all the general registers, will not generate any epilogue before that, and then restore them on exit, right? Good. This is what Philip tells you to do. Like if you go to his blog, you will something like printing to the console, but we will do something like find the. Sorry, just I wanted to find an entry which was like CPU exception. So here, for example, he talks about it a lot, that's his interrupt descriptor table. And essentially, where is this convention? He argues that that's the way to write. So you write a function like that, right? So far, so good. And looks very elegant. There is a caveat here. The caveat is the following. The calling convention saves and restores general registers and passes them as the stack. Actually, it passes a slightly different one. Do you remember what this argument interrupts that trade?
Aren't those the 544 registers that the CPU automatically pushes?
Correct, exactly. Which is a little, or it feels a little awkward because you say, look, what Philip is advocating you to do is he says, okay, the hardware pushes these 5 things on the stack, and the convention which he pushed into the Rust language, if I understand it correctly, will take this as this and pass it into the function as this argument, interrupt stack, right? So what does it mean? It means that inside the handler, you have access to the interrupt stack frame, meaning that these 5 things and potentially the error code, the 6th one, which are pushed by the hardware, but you don't have access to those registers, right? Because the compiler saves them and restores them, but it doesn't pass them to you as any of the arguments. Because I agree with you that this one also it doesn't talk about general purpose registers, right? Okay, so what's the logic here? Philip's logic was probably that majority of the interrupt handlers don't need to access those registers, right? Well, because you say, look, why do you need user RAX register? Because if you wanna use pass user arguments on the stack, then this RSP is saved by the hardware. So maybe that's enough, right? Unfortunately, I kind of disagree. So like for different purposes, you do need, first of all, maybe your ABI with user syscalls is different and you passing arguments in registers, right? And I think Linux does it, like Linux does pass some, like at least syscall number, x86 passes syscall number in register RAX, right? So you do need to access those registers in your handlers, at least in your interrupt handler, right? Maybe exception handlers don't, but exception handlers also need those information because you sometimes want to dump, if you like have a page fault, you really want to dump all of this, all of the user registers on the screen for debugging purposes. Make sense? like just to say, look, you crossed and your RAX was such and such, right? Okay, so that seems like a great idea to lock yourself into this x86 interrupt convention. Although, like, it seems like a fine idea. I'm not sure why they don't say, look, let's pass all of this general registers plus those registers and take like this, the interrupt frame should contain both, but they didn't do this, right? So what's the solution then? At least we understand that this is not an ideal case. I mean, I'm just explaining it because I'll deviate from how Philip does it in his blog. That's my reason. So I want to control what gets saved and what gets restored and how it gets saved, right? Okay, so Rust allows you to write those naked functions. And like there are multiple ways to do it, right? First of all, you can say, look, I know how to hack assembly, so I'll just create a bunch of assembly trampoline stops in pure assembly. I will be saving whatever I want to save. I will push all the registers. Like if this is already saved by the hardware, I will push those. Like if I have a function which takes 2 arguments, one argument is a pointer, for example, this one, and another pointer to general registers, I will be using a standard Rust API, which is like RDI and RSI registers, right? And everything from there, right? So you can hack it in assembly. That's totally fine. Rust gives you a slightly more elegant mechanism. It's called naked functions. You also label a function as naked. And then the assumption is that the compiler does not generate prolog, does not generate epilog. And I think the entire body of this naked function is just assembly code, right? And so that gives you control of how you save and what you save and how you go about it. So let me show you an example of how it can be done. I quickly can find it. Zafang actually does a couple of mistakes here, but essentially he uses, again, a macro to wrap pure Rust implementations of this into this macro, but the essence of this is the function, which is, it says extern C, so do not like mangle names or anything. It's labeled as naked. And after that, like you use this naked asm. He, for example, says, okay, disable interrupts. That's not entirely sure why he does it, because you can always control it here, so probably don't need it. After that, he saves all the general registers, essentially, and says, okay, I will push the top of the stack. I will move it into the RDI, which becomes the first argument to this function, right? So essentially, he makes the following compromise. He says, okay, for whatever reason, he says, my functions, my handlers will have access to all general registers, but apparently will not have access to the 5 saved by the hardware, which is not ideal either. So ideally, you should like write some code here which saves both and passes one as inside RDI, passes another inside RSI, right? Makes sense? And his types are like essentially, if we look at this macro, hopefully it will show up very fast. No. Back here. Not here, just true exception IDT. Show you like essentially, where is it? No. How do I quickly search here in the repo? Should be on top. What do we do? How do we search in a repo? Just this.
So 2 more matches. Below the code snippet, so 2 more matches.
Show more matches. Like something like this is a good example. So he says, look, I have a C implementation of this breakpoint, and I assigning it to the entry in the IDT. Everything is again well typed. So there is a specific entry in the IDT, which is a breakpoint. And there is a set handler function which assigns it correctly, like marks that it's available. But essentially he wraps it into in this assembly prologue and epilogue, right? With this naked assembly. Make sense? So we're almost there. There is still a slight subtlety here. The subtlety, I mean, I don't specifically like how Japan did it. I mean, I don't like what Philip is pushing because it just locks you into this convention. I think it's too restrictive. So at least let's use the naked assembly pass. What I don't like about the Japan is that he loses this, right? So he says, I'm not going to give you access to those fields. And he actually, which is kind of weird in his code, that he mixes and matches. Like, for example, this is wrapped in his assembly, but the invalid opcode, he doesn't wrap. So he uses x86, Phillips x86 interrupt convention. Maybe he was lazy, maybe he ran out of time, but ideally you should like choose one. But ideally you should say, look, I want to pass all of it. Like you define a new data structure, which has both these 5 things plus the error code and all the general registers, and then your assembly code should make sure that all these fields are initialized, right? Make sense? And then you save everything on the stack, you pass a pointer to the top of the stack as an argument, and then inside the Rust code you can access those individual fields, right? The subtlety is the following. Imagine we roll this assembly code like Jafang did. Just duplicate this. Like this one, make tasks and everything like is rosy. And imagine we also want to create a data structure which has 5 fields, error code, and then all general registers, general purpose registers, right? General. How do we go about the fact that these two are only pushed when you transition from 3 to 0, and not pushed when you transition from 0 to 0? And how do we? Error code is easy because you say, look, depending on the type of the handler, we'll use 2 assembly implementation, and he has a second one, wrap interrupt and wrap with error code. This one contains a mistake, but essentially he has to push an error code somewhere here as well. He doesn't, but because he just does the registers, right? But essentially, you got the point. So this is not the problem. The problem are these 2 fields, which are stack segment and RSP. They are only pushed when you transition from 3 to 0, and they are not pushed when you transition from 0 to 0, which means that your data structure might, if you say, look, I will pass this as an argument into my interrupt handler, like whatever, it's like foobar handler, then maybe those 2 fields are either not initialized or maybe even like dangling somewhere in memory, right? Because what if the stack was starting from here at the beginning? Okay.
Is it aren't the values pushed by the hardware aligned to a certain, like a 16-byte address, and then you could use that to determine how many?
I don't think so. Hardware will just push. If this was your pointer, like from where is it? So like TSS is the pointer to the kernel stack. So imagine this pointer flows right here, then it will just immediately start. Maybe it will just create an exception. Maybe you're right, and maybe there are some alignment rules, and if it detects that it's unaligned, that it just immediately throws an exception and just like double fault at this point, right? Maybe, but let's assume it's aligned to the page boundary at least. But
since we're defining all of the interrupts for VOS, what is stopping us from only pushing and popping the registers we actually use for specific? Is that not even worth doing? Or
no, hold on. There are 2 things here. You may have a compiler which says, okay, the kernel never touches RAX register. like through the entire code base of the kernel. It's easy to build, just whatever, patch LLVM, right? Then you don't have to save RAX. You say user can use RAX, but the kernel will not. This is rare because you lost a register and there is no real reason to do that, which means that most likely, like the probability of the call chain through the kernel not touching a specific register is very, very small, right? So you probably have to save them all the general purpose registers, at least.
It's because
Right, yeah. And they're big and they can context switch and everything. But the first 5 are saved by the hardware. We don't control the hardware. Hardware has a protocol. If it transitions from 3 to 0, it will push this 2. If it doesn't, it will start pushing from this, which means if you have a data structure, these 2 fields might be dangling. So how to go about it? You got the problem at least. How to go about it is a little harder. Okay, insight for how to go about it. 2 more minutes.
Could it happen when we hit the GDT? Like accessing the GDT will be there.
Hardware, like I explained you all the hardware. Hardware will not do anything for us at this point. Yeah, let's.
Rearrange so that the dangling part's on the top. But if we can figure out if it's dangling or not, then we can pop it.
Yeah, and that's really the reality of life. It's called, I think it's called normalization of this interrupt stack. I mean, you can make different assumptions, and that's what I don't like about Philip, that he doesn't discuss it. But okay, if you start discussing, then you go into so many bushes that only us can tolerate it, right? He doesn't mention it even, I think. Maybe he does, maybe I missed that. The idea is yes, it's a real pain in the butt. The real problem, the real solution is to write assembly, as you say, which you are inside the interrupt, you say, look, I don't know what happened. I don't know my past. I don't know whether I'm coming from ring 3 or 0. Like you say, reserve some space for whatever, for 6. That's the max we need because it's an error code and whatever the other 5s. Then maybe save all the other registers as soon as you can, right? General registers. And then write some custom code which figures out whether you transition from PL3 to 0 or from PL0 to 0, right? And this custom code, because registers are already saved, can use all the registers. You can essentially, you have to inspect CS value, which got saved on this stack somewhere here, figure out whether you're transitioning from 0 or not, and then fill in those fields, saving them manually, essentially normalizing the stack, and then pass this pointer as a pointer to your handler, right? And this is what Linux is doing. In Linux, the code is written in such a manner that good luck to you understanding it, but there is a guy who wrote almost a book about it, so he explains how every line of this entry code. But this is essentially the idea of normalization. You have to do it in software. If you're like building a real operating system, you have to do it in software. I think it's okay to make, like in Philip's thing, it's the same. So like these 2 fields can be potentially dangling. And the crate says that those 2 fields are only valid when you transition between privilege levels. Okay, good luck to you reading the crate specification carefully to say that, to figuring out that the fields are valid.
Why would Intel do this? Seems
Good question.
complicated.
Why? Yeah, probably just a silly mistake. Maybe they wanted to save, I don't know the history. Maybe they wanted to save stack space or something. Maybe back in the days, you know, every byte of a stack is valuable, like on embedded systems. But yeah, it's such a pain just because of this. And imagine, like on top of all this normalization, imagine you didn't disable interrupts and another interrupt arrives here. That's crazy. And that's why probably we will go the route of disabling interrupts. Maybe we'll not even normalize the stack and just assume that we will never touch these 2 fields. Safety, it's whatever. Everything is as safe as we define it, right? But okay, we got the point. And I will explain one last thing next time, and after that, we're ready to go. I'll try to assign the homework even before we reach Monday. Slight thing, Monday I will be here, Wednesday I'm traveling. I'm actually on a plane during the lecture time. So that you will be working on homework. Let me stop here because I'm over time. Okay, so last time, like next time, just one final explanation for interrupts. I hope I will push the homework right today or tomorrow. And sorry, previous homework is almost ready. You will be able to push it soon as well.
They can push it now.
Oh yeah, so Soham, who was helping me with the auto grader, says I'll send an email. So please submit. And again, like there is no penalty for anything. Like as long as if it doesn't work, I will maybe let you know and say, guys, we want to fix something, make sure that it works. But essentially, we will start on building the interrupt infrastructure for this little problem.
But it accepted this. Yeah, but it told you it failed.
Totally failed.
Yeah,
Said there wasn't
yeah.
a file.
Oh, it said there weren't any.
Weren't any file. I was trying to do a copy that failed and then try to do a make docs, which obviously.
Right, yeah, so, that part we're still figuring out, I'll write up something about the exact.
Oh,
You were able to.
Могу забрать эту машину.
I think grade school still doesn't.
Ого, прям, спасибо большое. Так, машина уже дома, то есть я еду домой.